Okay, so hello everybody, my name is Sebastiano Miano, and today I will present this work called Securing Linux with a Faster and Scalable iptables. So, as we all know, today iptables is one of the most used software, with a huge number of applications that rely on it to apply different security policies to the traffic or to filter packets according to a specific set of configured rules. However, with the transformations of applications that are running on data center in favor of microservices or more generally cloud native applications, and also the increase of network speed, it became more evident that the performance of iptables are quite slow. In particular, when a high number of rules are used, which is something typical in such environment. So the main goal that we set for this project was to try to improve the performance of the existing iptables kernel implementation in a way that is transparent to the existing applications. So while keeping the same semantic and syntax of the original iptables. On our attempt to solve such performance issues, we select the extended Berkeley packet filter as a base subsystem to build such iptables clone. eBPF is an extension of the already existing Bpf virtual machine, which allows user to write and to generate and inject custom defined programs into a running kernel without having to install additional kernel modules or to rely on custom compiled kernels. eBPF programs can be attached to different points of the TCP/IP stack, for instance at the XTP layer, where packets are processed directly at the driver level before the allocation of kernel data structures. So in this talk, I will present an high-level view of Bpf-iptables, and in particular the main challenges that we had to solve and the most important design decision that we had taken. So the first goal of Bpf-iptables was to preserve the original iptable semantic. Of course, if we want to provide a clone of the existing iptables, we cannot create differences in the way packets are filtered by the two softwares, no? Because differences could create serious security problems for applications that transparently use our Bpf-iptables clone instead of the original iptables. However, iptables filter packets on the Netfilter framework, and these packets are filtered in the input, forward and output chain, depending on whether the packet is going to a local process, is going to a remote destination, or is generated by a local process and is sent out of the host. However, on the other hand, eBPF programs are attached to different points in the TCP/IP stack, in particular in the TC ingress and TC egress hook and the XTP ingress hook. Such hooks are different than the Netfilter hooks, so we cannot, while on one end we can filter packets before in the TCP/IP stack, on the other hand we cannot use the routing decision that is in the Netfilter framework. So, in order to solve this problem, we created two different eBPF programs in our Bpf-iptables pipeline, which is an ingress chain selector and an egress chain selector. The first one is attached to the eBPF ingress hook and is executed when a packet is received on the host, while the egress chain selector is attached to the eBPF TC egress hook and is executed when a packet is going out from the host. So both eBPF program parse the packet and extract the source and destination IP of the packet, match this packet against an eBPF, this information against an eBPF map, which contains the information if that source or local IP address is or source or destination IP address is local or remote. This eBPF map is filled by the Bpf-iptables control plane, which is also listening on netlink messages on changes on the Linux routing table in order to update accordingly the eBPF map with the new information. So the second goal of Bpf-iptables was to improve the original iptables classification algorithm. Iptables uses a linear search algorithm to find the rule that matches a specific packet. And this is, let's say, is the main source of overhead for the classification of iptables. In order to select this new classification algorithm, of course, we looked at the literature, and there are many existing classification algorithms. However, we had to face and to find a classification algorithm that was feasible with the eBPF constraint, in particular feasible with the available eBPF data structure, and also feasible in terms of number of instructions required in the eBPF program, and also the type of operations required. At the end, we select the linear bit vector search, which is, let's say, a quite old classification algorithm, but that has proved to be very effective for the eBPF-iptables use case. So this is the Bpf-iptables classification pipeline, which is in charge of filtering packets according to the rules configured for a given chain. The classification pipeline is made by a set of different eBPF programs, each one handling a single matching protocol field of the rule set. The pipeline contains a percipue shared map with a bit vector that represents the entire rule set. This bit vector has a bit set to 1 if the packet has matched the rule the position where the bit is set to 1, or 0 otherwise. So each module of the pipeline basically extracts the needed packet field from the packet and performs a lookup on its private eBPF map to find the associated bit vector with the current packet value for that field. Now, if the lookup succeeds, the bit vector retrieved from the lookup is matched. We perform a bitwise end-to-end operation with this bit vector and the one retrieved from the shared map, which is saved by the previous programs in the pipeline. And then, when we reach the end of the pipeline, the final program retrieves this bit vector from the percipue shared map and looks for the position of the first bit set 1 in the bit vector, which is the, let's say, the highest priority rule that has matched the current packet. Finally, it retrieves, let's say, the action associated with that specific rule, which can be drop the packet or accept the packet. Now, another goal that we set for Bpf-iptables was to support stateful filter. Bpf-iptables, as for iptables, as the necessity, we want to, let's say, support the possibility to track the state of TCP, UDP, ICMP connection, as it is done by the Netfilter framework. However, Bpf-iptables is executed before Netfilter, so that means that packets are classified and dropped before the Linux connection tracking is even hit. To support stateful filter, so we had to implement our own connection tracking module in Bpf-iptables, as we can see in this figure with the overall architecture, with these 3 different additional components, which are connection tracking label, the connection tracking update, and the connection tracking table. The connection tracking label is in charge of understanding which is the next state of the connection based on the current packet values. And then, if the packet survives the classification pipeline, the connection tracking update module is in charge of committing the new state in the connection tracking table. So finally, we also evaluated the performance of Bpf-iptables, comparing them against the iptables and Nf-tables in kernel, let's say, implementation. As we can notice, the performance of Bpf-iptables are considerably better than the other in-kernel alternatives. And this is mainly given by, first of all, the early stage where packets are filtered by Bpf-iptables, which are the XTP and the TC hook, and also the improved classification pipeline that we implemented within Bpf-iptables. So finally, to conclude, we can say that Bpf-iptables has demonstrated the huge advantages over existing solutions without requiring any change to the existing kernel, so relying on upstream or vanilla Linux kernel. We can say that latest eBPF improvements can also be ported to Bpf-iptables, so in particular increasing the number of supported rules in the rule set. We tested with 64K rules and the performance were still better than the existing in-kernel solution. There are several performance improvements in Bpf-iptables which depend on the runtime configuration, which I didn't mention in this talk, but that you can find in the paper, and are possible thanks to the dynamic injection and recompilation of eBPF. So finally, I just want to mention that Bpf-iptables is part of a bigger project, which is Polycube, which is completely open source. And allow us to create, let's say, more complex application, very complex applications with eBPF, chaining different network functions together. So that's all. Thanks for the attention. And of course, now I will be happy to take any questions that you have.
All right, thank you, Sebastiano. So we don't actually have questions in the Slack. No here. So hopefully we'll get some at some point. And in the meantime, I was actually wondering, so you mentioned a lot about, the fact that you work on eBPF. What are the alternatives? You muted.
Yeah, sorry.
Yeah.
Yeah. So you mean what are the alternatives actually to build, let's say, an in-kernel application, no? So let's say with eBPF you have the possibility, the great advantage of having the same development cycle of user space applications. Of course, the other alternatives will be just modifying the current iptables implementation in the kernel, but this would require an agreement with the Linux community. In addition, if you want to implement, let's say, a custom classification pipeline or a custom protocol to filter packets, you cannot do it. No, you have to agree with the kernel community that the solution that you are applying is general enough for every type of workload. The good thing with the eBPF is that you can write your own application, which is running in the kernel as it is for a kernel module, but with the difference that you can customize your application as you want. So you can also write your classification pipeline, which is performing better probably for your own workloads or for your own tasks.
Okay, so we've got actually a question on Slack from your current boss. So there is lots of workaround offloading, and some people go for smart NICs, others for eBPF or EFXDP. Now, can you give us a bit of light where eBPF is the best choice? What is it the best choice for, in your opinion?
Okay, I swear that we didn't agree the question. Actually, is a difficult question. No. So let's say there is the possibility also to enhance the classification pipeline that we implemented with eBPF-iptables, also with smart NICs. In particular, if you look at the paper, we implemented some optimizations where if you write the rule set in a specific way, it is possible to take some of these rules and put them at the front of the pipeline. That means that if you have also a smart NIC that is able to handle or to filter packets directly in hardware, you can offload automatically or transparently those rules directly in the smart NIC. So the great advantage will be that you can filter, you can drop packets at faster rates. So this is also one of the most let's say used use case for eBPF with the smart NIC. So
So
yeah.
in what case would your solution be best in terms of environment versus a hardware accelerated one?
You mean without having the hardware? Let's say if okay, so the question is without having the hardware, without having a smart NIC, in which case the solution will be the best?
Yes, what context, what environments, you know, for whom do you want to set that solution basically?
Okay, let's say that in probably in a limited resources environment where you don't have smart NICs available, you can directly use software processing, no software filtering just to filter packets. So in such cases, it will be better to just use the eBPF-iptables software implementation instead of the enhancement with the smart NIC.
Okay, thank you, Sebastiano. And to start the questions, so eBPF essentially provides hooks in the kernel, right? So to make it easier to program, right? But somebody has to place these hooks in the kernel. So who's going to do it, and whether the person who can do it will be willing to do it?
Yeah, that's a good question actually, because let's say currently in the eBPF environment, no, these hooks available at least for the networking part, no, because eBPF, let's say, is a bigger framework where they give you the possibility to attach a program to every type of kernel function. So generally, you can attach an eBPF program as after the execution of any generic kernel function. But for the networking purposes, there are mainly two different eBPF hooks, which are the XTP hook and the TC hook. So as you said, these hooks are already defined in the kernel. So there should be an agreement from the kernel community that a new networking hook is required. Indeed, when we started this work, we were thinking to, for instance, create a new hook inside the Netfilter framework, because Netfilter is the place where packets are filtered by iptables. And since we want to improve the iptables classification pipeline, another possibility was to attach a program to the Netfilter hook. But then we selected another approach that was, okay, let's deal with the current Linux kernel, with the current vanilla version. So we don't have to add a new version to modify the existing kernel. And let's put our eBPF program in the already existing hooks, which are these XTP and TC. And these are actually proved to be very performant, since the existing hooks are executed before Netfilter. But on the other hand, we had to, let's say, face additional challenges. For instance, we had to create our own connection tracking, since we couldn't exploit the already existing connection tracking on the Netfilter framework.
Okay, and another question is a bit more general. So stepping above eBPF, but thinking about what it's trying to achieve to promote innovation. So there are alternatives, right? So right now there are various prominent efforts like Quick, where things done in the user space. So how would you compare these two approaches? Just don't worry about the kernel and do your networking programming over UDP with much bigger flexibility, as opposed to try to do something in kernel with using these hooks?
Well, I believe that, let's say, before the introduction of the eBPF, definitely building applications in kernel was very difficult, no? Because you had to create your own custom kernel modules. For instance, OpenBooSwitch is an example, no? If OpenBooSwitch, at least the kernel data path, no, relies on a custom kernel module, then OpenBooSwitch maintainers complains a lot about, oh, we need to maintain this kernel module, it's very difficult. With the introduction of eBPF, this has became very, easier to inject functions or additional functionalities in the kernel. So I believe that probably in the future it will be interesting to explore the possibility to, let's say, put some additional logic in the kernel by using eBPF, while more complex operations, such as the one required by Quick, should be still handled by the user space. So I believe that probably an hybrid approach where you have a Linux kernel stack which can be, let's say, modified or customized without touching or creating a custom kernel module would be the right choice in the future. At least,
okay.
Yeah, what we believe.
Okay, well, one good thing about the future, nobody can predict it, so we don't know how it's all going to go. In regard to technical issues or how the conference will take place. So it's never easy to be the best in anything, so congratulations on getting the best technical paper of the last year of the CCR.